Hello everyone. In this session, we are going to study the determination of hardness of water by EDTA method, and this is a complexometric titration method. Complexometric titration because in this method there is going to be a formation of a complex in the reaction. So first let's have a look at what exactly EDTA is. So EDTA is a organic compound where E stands for ethylene group. Here you can see at the center, this is the ethylene group, CH2 single bond CH2. D stands for diamine. So you can see each carbon of the ethylene group is attached to a nitrogen atom. So, and there are two nitrogen atoms, so it is diamine. T stands for tetra, that means 4, and A stands for acetic acid. So you can see each nitrogen atom is attached to two groups of acetic acid. So this is the acidic group. There are 4 groups. So EDTA is a hexadentate ligand. So ligand in general is any molecule which can form bonds with metal atoms by its donor sites. So you can see there are this green color, these are lone pair electrons on nitrogen. Even oxygen has a lone pair of electron. So if heterogeneous atoms have lone pair of electrons which they can donate to form coordinate bonds. So that is why EDTA is a hexadentate ligand. That means it has 6 donor sites. It can form a coordinate compound with a complex, or I can say coordinate complex with a metal atom. So we will see the structure of the complex ahead. Now, in this titration for determination of hardness, instead of using EDTA, we use its disodium salt. So the structure of EDTA and its disodium salt is similar, just the difference is that in disodium salt of EDTA, two hydrogen atoms of two acetic acid are replaced by the sodium ions. So this is disodium form of EDTA. And as this titration, we are going to use disodium form of EDTA instead of EDTA because it is more soluble in water. Since this is more soluble in water, it can easily react with the hardness causing metal ions in water. So let's have a look at the principle. So we know that if there are salts of heavy metal ions, so the metal ions which are present in the group 2 of periodic table, mainly calcium and magnesium. If there are salts of calcium and magnesium present in water, that water would be hard. So the main principle is that these ions, calcium and magnesium ions, if they are present in water, they form a complex with the indicator. So this is a titration. So we do need an indicator so that we can see the endpoint of the titration, so that we can find out the endpoint. So the indicator which we are going to use in this titration is Eriochrome Bracte indicator. So this indicator also forms a complex with the metal ions. So therefore complexometric titration, as well as the solution, the chemical which we are going to use, disodium form of EDTA, it also forms a complex of the metal ion. The difference is the complex which is formed between metal and indicator, it is a unstable complex, while the complex which is formed with disodium form of EDTA and metal ions, those are the stable complex. So we will see this is the driving force for the reaction to take place, that the unstable complex will be broken and a stable complex would be formed. So we will understand this further. Also for this, for the endpoint, to understand the endpoint of the titration, we'll have to see a color change. So the color change in this would be from wine red to blue. So why wine red to blue? We'll understand that. First, let's have a look at the complex which will be formed between disodium form of EDTA with the metal ions. So you can see this second image. This is the structure of the complex. As I said, disodium form of EDTA or EDTA is a hexadentate ligand. Why? Because it is going to form 6 bonds with the metal ion. You can see there are total 6 bonds which are formed with the metal ion by the disodium form of EDTA. So this is a hexadentate ligand. That means it has 6 donor sites with which it can form the coordinate complex. Now let's have a look what exactly is going to happen in the titration. So in conical flask, we are going to take a water sample whose hardness we need to find. Plus in this we are also going to add the indicator. So indicator is EBT indicator, Eriochrome black tea indicator, which is blue in color. But as soon as you add that indicator into this water sample, the color changes to wine red. Why? Because it indicates that the complex is formed between metal ions and the indicator. And then from burette, we are going to add the disodium form of EDTA until this color, wine red color, changes to blue. Okay. Plus, we are also going to add a pH 10 buffer solution into the conical flask. So, why we are going to add it? We can understand it with the help of a reaction further. So this is the end point. When you take everything into the conical flask, that is your water sample, you add 1 or 2 drops of EBT indicator, which is originally blue in color, plus you add a buffer solution of pH 10, you will see that the color you can see in the flask is wine red. And in this solution, you add EDTA from the burette until the color changes to blue. Okay, so when the color changes to blue, the endpoint is achieved, and then we can do the calculations for finding the hardness of water. So what are the reactions which are taking place? So as I said, in a water sample, M indicates the metal ion, hardness causing salt of metal ions which are present in water. So M is going to indicate the metal ion, whether it is magnesium or calcium. In that, we are going to add the EBT indicator, organic indicator, which is actually blue in color. Plus, in that, we are going to add a pH 10 buffer solution. We can see that the color of the solution changes to wine red. That indicates there is a complex form between metal and indicator, plus H plus ions are given out. So we know that as the concentration of H plus ions increases in water, acidity is going to increase. So we need to maintain the acidity for the reaction. That is why we are adding pH 10 buffer solution in the conical flask before only. Okay. Similarly, Na2 EDTA, that is disodium form of EDTA, also forms a complex with the metal ion in presence of pH 10 buffer solution, means when we maintain the pH. The difference between this complex and the first complex is that the complex between metal and EDTA is more stable as compared to metal and EBT. So this is the driving force for the reaction to take place. So this is the overall reaction, that we have a wine red color solution in a conical flask. In that we are going to add Na2 EDTA drop by drop under pH 10, means under when the pH is maintained to 10, that is, this is also called as ammonical solution, pH 10 solution, until that wine red color changes to blue. So what this indicates actually, that the metal indicator bond gets broken and a new complex is formed between metal and disodium form of EDTA, and our indicator gets free. So that is the color change from wine red to blue, because the original color of the indicator was blue. So how this is actually performed in a laboratory? So it is performed in two parts. First part is standardization of disodium form of EDTA. Standardization of EDTA means we need to find the concentration in terms of molarity for EDTA. Standardization is finding the actual accurate concentration, or you can say molarity of EDTA. How it is done? By titrating EDTA with a known volume of known concentration solution of MgSO4. So we take magnesium sulfate in a beaker instead of water in first part, of known volume, suppose 25 ml, of known concentrations, that is molarity, suppose it is 1 molar or 0.01 molar, and we titrate it with EDTA. We add EDTA into it drop by drop until the color changes from wine red to blue, because we are going to add everything, that is the indicator, pH 10 solution in the conical flask. Just instead of water you take MgSO4. So you know molarity of MgSO4, you know volume of MgSO4, you know the volume of EDTA which is required for changing the color from wine red to blue, and by cross multiplying you calculate M2, that is exact concentration of EDTA in part 1. Now part 2 is to calculate the hardness of water. So for calculating hardness of water, this is the method which is used, that is the molarity equation is used. That is 1 molar 1000 ml EDTA is equal to 1 molar calcium carbonate equivalent of hardness. So we are comparing it to calcium carbonate because we know that hardness is measured in terms of calcium carbonate equivalent. Then we have taken 1 molar 1000 ml EDTA would be equal to 100 gram of calcium carbonate equivalent, because we know 1 mole is equal to molecular weight in grams of a compound. So 100 is the molecular weight of calcium carbonate. We have calculated it in the previous session, so you can refer my previous video. And then now we are going to calculate it for we have to generate a generalized formula. So we are assuming, not instead of 1 molar, we are saying suppose it is M2 molar, which we have calculated in the first. M2 molar V2 ml EDTA would be equal to Sx gram of calcium carbonate equivalent. Okay, so since we know that for M2 1 molar 1000 ml EDTA is equal to 100 gram of calcium carbonate, we need to calculate if we have taken M2 molar V2 ml of EDTA, then X gram of calcium carbonate equivalent hardness would be present in water. So we are simply going to calculate the value of X by cross multiplying. So X would be M2 into V2 into 100 divided by 1000. So this two equation we are using. Okay, gram of calcium carbonate equivalent. Now 1000 is below. Okay, so if we take it above, it will be 10 raised to minus 3, so it gets converted into mg, milligram. Now for water sample, we know we have taken vml of water sample. Okay, so if we have taken vml of water sample, then what would be the hardness? So vml of water sample, it would be V2 into M2 into 100. So we are going to calculate it for 1 liter in generalized formula. So if vml contains this hardness, then 1 liter, that is 1000 ml of water sample, will contain how much hardness? So again, we are going to relate these two equations and find out the value of X, which would be actually 1 into V2 into 100 into 1000. That is, means either you can consider if in liter 1 or ml, it would be into 1000 upon V ppm of CaCO3 equivalent. So in previous session, we have seen that 1 mg per liter of calcium carbonate equivalent is equal to 1 ppm of calcium carbonate equivalent. That is why first we were using the unit mg, but we can also use it as ppm. So this is the main formula which you need to remember for calculating the hardness of water by EDTA method. Okay, so this is it. So mainly you need to remember this formula for calculating hardness. So in next session, we will see how practically this formula can be used for calculating temporary, permanent and total hardness of water. Also, for much more clarity, I am sharing a link of practical demonstration of finding hardness of water by using EDTA method. So in that video, you can see how it is done experimentally in lab for more clarity. Thank you.